Hello everyone. So today's lesson is dealing with these two words that are a little weird, but we've talked about one of them before, and it's really not that difficult conceptually, so it's not too bad. So enthalpy and entropy. So enthalpy is really just your heat in a reaction. We can think about that as our delta H, and we did this already. Delta H equals the heat of the products minus the heat of the reactants. And the term spontaneous reaction is going to come up here. So all that is a reaction that proceeds on its own without any outside intervention. So you don't have to do anything to get the reaction going. Once those two substances come in contact with each other, or whatever, how many substances are in the reaction, once those reactants come in contact with each other, the reaction occurs. So you don't have to do anything to get it going. It just happens all by itself. That's a spontaneous reaction. So enthalpy, just think of that as our energy in the reaction, our heat content. So it's products minus reactants. So we did all this already. Negative delta H is exo, positive delta H is endo. And here's how these look on our PE diagrams. Exo, energy is exiting. You're ending up lower than you started. Endo, energy is entering. You're ending up higher than you started. So that's all we really need to talk about for enthalpy. It's just think of it as delta H, pretty simple. So your entropy, we got to spend a little bit of time on. So entropy is a quantitative, a quantity, an amount, but we're not going to assign any numerical values here. You just got to do a relative comparison, and it's really pretty simple. So it's a measure of the disorder or the randomness in a substance. So entropy is a measure of disorder, and the symbol is S. So I like to think it's our sloppiness. Entropy is your sloppiness, how sloppy or unorganized something is. So the larger the disorder, the greater the entropy. So you got to think of it as disorder, unorganized. So nature likes disorder. Nature likes sloppy things. It takes work to keep things nice and neat. So most spontaneous reactions have a decrease in energy and an increase in entropy, which means more unorganized. So nature likes stable, which is our low energy, and sloppy. Nature likes stable and sloppy, right? It likes things to have low energy. It's when they'll be the most stable, so exothermic reactions are favorable. And it likes things with a lot of disorder, so increased entropy, higher entropy. So nature likes stable and sloppy. So low energy, high entropy, okay? So that's entropy. So how do we measure entropy in a reaction? We're really going to focus on two things here. One is the phase change. And we've done this a million times. We did this back at the beginning of the year. So here's our phases, solid, liquid, gas. And we're just adding solution in here because most of the solutions that we deal with are liquids. So we're going to stick those right in between liquid and gas. And if we remember our trend from back in the beginning of the year, the most organized phase is the solid phase. So that's going to have a low entropy, a low amount of disorder. And the most unorganized phase is the gas phase. So that's going to have a high entropy. And it increases as we go across. So if I have something like this, carbon dioxide going from solid to gas, our sublimation. All you got to do is say, all right, it's going from solid to gas. It's going from an organized to unorganized. My entropy is going up. That's it. That's all you have to be able to do. Say, is the entropy going up or is it going down? Really very simple. So the other factor we want to include in our assessment is the amount and types of particles. So more particles means higher entropy. It's more unorganized. So the more stuff you have, the harder it is to keep it organized, and the more it's going to tend to become a mess. So that's the way you want to kind of look at it. If I have a drawer with one thing in it, my marker, it's pretty easy to keep that drawer organized. It's one marker in it. But if I have a bunch of different things in there, it's going to be a lot harder to organize it. If I have my keys, bunch of pens, pencils, erasers, rulers, all this stuff in there, it's a lot harder to keep it organized. So the more particles, by the nature of that, you're just going to have greater disorder. So higher entropy. And also a greater variety. More different types of particles is going to lead to higher entropy. So again, think back to my draw. If all I have in that draw is not just one marker, but a bunch of these exact same markers, it's not going to be that hard to keep the draw organized because it's all the same thing. But if I go back to my draw full of all different things, now it's a lot harder to keep it organized. So just kind of think about it practically, and all you have to be able to do is a relative comparison. So here's an example. So I have 2 moles of aluminum chloride as a solid is reacting to make 2 moles of aluminum, 3 moles of chlorine. So we're making different substances. They're in different phases. So what's happening? It's becoming more unorganized. My entropy is going up. That's all you got to do. So you're going from one substance in one phase to a bunch of two different substances, 2 different phases, more variety. That's going to lead to more disorder. So your entropy is going up. So those are the 2 things we want to use to make our relative assessment here. All right, it's really not that complicated. So let's look at this worksheet right here. So you should have this, download it, print it out, just bring it up on your screen and go through and do these and see how we do. So all I want you to do is look at the whole reaction. So look at big picture and say, well, what do we think is going on here? All right? So the first one, I have one substance in one phase breaking down into 2 different substances, 2 different phases, so it's becoming more unorganized. My entropy is increasing. So that's all I really want you to do is tell me, is the entropy increasing or decreasing? So the next one, easy. One substance is not even changing. All that's going on is going from liquid to solid. So think back to our factors. Phase is going from a more unorganized to a less unorganized, so my entropy is decreasing. Liquid to solid, decrease in entropy because we're becoming more organized. That's it. So just look at the rest of these. Try and just don't think about it too much and focus on one substance. Look at the big picture. Does it look like it's becoming more or less unorganized? So take a minute, answer these questions, and then we'll go through them. So here are your answers. So take a minute, check these out, see how you did. And that's pretty much it. So if you want to look at some of these, the ones where we're going into solution, think about where we put solution in our scale from solid to liquid to solution to gas, becoming more unorganized. So if solid is dissolving, my entropy is increasing. So anytime you're forming a solution, it's increasing. Number 10, we're coming out of solution, so now we're going backwards, we're decreasing. Same thing with number 7. So it's not too bad. Some of these you got to kind of look at and eyeball and say, where do I think I could go? I kind of go either way. Number 8. For number 8, we have a solid and a gas going to a gas. So we have 2 different substances, 2 different phases becoming one substance, one phase. So I would say it's decreasing. But if you said, wait a second, it's solid and this is a gas, now it's all gas. Gas is unorganized, very random, high entropy. I think it's increasing. So I mean, for this one, I could understand how you could go either way with that, but you're not going to really see anything where it's that up in the air. It's pretty cut and dry. So don't overthink these questions. Just tell me if we think the entropy is going up or it's going down. Look at the reaction. What do you think? Entropy is your disorder. It's your sloppiness. It's how unorganized something is. And that's that for that lesson.